In our first related rates example, we're going to look at the rate at which the depth is changing as water drains from a conical tank. So with every related rate situation, the first thing I'm going to do is get a sketch of my situation. So in this situation, we have a cone. We know the radius of the cone. It's 12. We know the cone has a depth or an altitude of 24. Next thing, we'll look at the information that's given to me. We're told it's being emptied at a rate of 6 cubic meters per minute. So that represents rate of change of the volume. And the height of the cone is 24, base diameter is 24. How fast is the water level changing when the height of the water is 10? So my objective, find the rate of change of the height, dH over dt. Okay, in modeling this situation, this is a cone, volume of a cone, 1/3 pi r squared h. Now, in some instances, we can take a derivative at this moment, which would require us to use the product rule. However, if we do so, we would then need to know what is the rate of change of the radius, which is not given to us. There's multiple ways to look at this. One thing that we can do is create similar triangles and write a relationship between the radius and the height. So by using similar triangles, 12 over r is 24 over h. 12h equals 24r. So we know that r is equal to 1/2 h. So now we have a relationship between r and h. Let's go back to our volume equation and make that substitution for r. Doing some simplification, 1/12 pi h cubed. So now we have the volume equation in terms of the height. So now let's take the derivative, look at the rate of change of the volume. And now it's just a matter of us plugging in all of our values and simplifying. So rate of change of the volume was -6. The current height, or the height at the moment, was 10. And our objective was to find the rate of change of the height. Simplifying this, we're going to have 100 divided by 4, 25 pi on the right side. Divide both sides by 25 pi. We get -6 over 25 pi. And let's label our units in meters per minute.